You know, when we picture manufacturing in our heads, I feel like we almost always default to the exact same image.
Oh, absolutely. It's always like the busy assembly line.
Right. We see, robotic arms welding steel car frames and this big shower of sparks, or maybe rows of people diligently sewing pieces of fabric together.
Yeah, we're kind of culturally conditioned to think of manufacturing purely as a story about putting things together.
Exactly. But today, we are actually going to look at the other side of the coin. Because the biggest bottleneck in a factory, and I mean, arguably the greatest opportunity to either lose a total fortune or make one, actually happens when things are being taken apart.
Or, well, more specifically, when raw materials are being cut.
Yes, cutting. So, welcome to the deep dive. We are spending some time today with a really in-depth industry guide and production breakdown provided by velocity plotters and cutters.
And this specific source material is great because it pulls back the curtain on a stage of production that, honestly, rarely makes it into the glossy promotional videos of big brands.
It's definitely not the sexy part they show on TV.
Right, but this single step dictates the success, the failure, and, the financial margins of every single process that follows it on the factory floor.
So our mission for this deep dive is to explore how one highly specific piece of technology, which is the automatic single-ply cutter, is just quietly revolutionizing everything. I mean, from the clothes you are wearing right now to the soundproofing interior of the car you drive.
It really is everywhere once you know to look for it.
But before we get into the heavy machinery of it all, I want you to imagine something. Think about the last time you had to cut out like a complex paper snowflake.
Oh boy, lots of tiny scissors.
Yeah, exactly. Lots of intricate little internal cuts, sharp angles, maybe some smooth, sweeping curves. And, it takes a lot of concentration.
For sure.
Now, imagine you have to cut out that exact same snowflake perfectly 1,000 times in a row, but you're using thick cardboard instead of paper, and you have to do it without your hand ever cramping and without making even a single millimeter of a mistake.
I mean, that is it's a physiological impossibility for a human being.
Right. Yeah.
By the 10th repetition, your attention is wandering. By the 50th, your grip strength is completely fading and your hand is probably shaking.
You'd just be ruining cardboard at that point.
Exactly. The blade angle changes, the cuts get sloppy, and the material just starts to fray.
And that physical limitation really sets up the absolute necessity of automated precision in modern manufacturing. But we kind of need to understand the mechanics of how this technology actually overcomes that human limitation, right?
Yeah, we need to look at the machine itself.
So the source material refers to this machine as a computerized CNC cutting system. Now, for anyone not spending their weekends reading engineering manuals, CNC stands for Computer Numerical Control.
Which is a very fancy way of saying a computer is steering a physical tool using math.
Right, mathematical coordinates. But I really want to understand the actual anatomy of this machine. If I walk onto a factory floor today, what am I actually looking at?
So you are basically looking at a large, flat, industrial table. Usually it's several meters long, with a robotic gantry suspended over it. And the entire workflow, it actually starts in the digital realm.
Okay, so it starts on a screen.
Right. A designer creates a CAD file. And CAD just stands for computer-aided design. You can kind of think of it as a virtual two-dimensional blueprint.
Got it.
Every line, every curve, and every notch on that blueprint is mapped to a specific mathematical coordinate. So when that CAD file is loaded into the cutter's computer, the machine now has like a perfect map of the geometry it needs to create.
Okay, sure, the computer has the map. But you still have to deal with the physical reality of the material itself. I mean, if you drag a blade across a loose piece of fabric or, say, a sheet of thin leather, the material is just going to bunch up or slide away from the blade.
Yeah, that's the classic problem. And the machine solves that physical problem with an incredibly powerful vacuum system that's built directly into the cutting table.
Wait, the table itself is a vacuum?
Exactly. The surface of the table is porous. So when the material is laid flat, the vacuum engages and pulls air straight down through the table.
Oh, wow. So it's like an air hockey table in reverse.
That is the perfect way to picture it. Instead of pushing air up to make things glide around, it sucks air down to create immense negative pressure. And that locks the fabric, or the leather, or the carbon fiber, rigidly to the surface.
So the material essentially becomes like a temporary, solid, immovable block.
It becomes completely stable.
Ugh.
And once the material is locked down like that, the cutting head goes to work. And this isn't just dragging a static razor blade around.
Right, it's not just a fancy box cutter.
No, not at all. The head often uses a high-speed oscillating blade. It moves up and down thousands of times a minute, acting kind of like a microscopic jigsaw.
Thousands of times a minute, that's intense.
Yeah, and because it is controlled by those CNC coordinates, the head knows exactly when to lift the blade, rotate it a fraction of a degree to navigate a sharp corner, plunge back into the material, and continue the cut. And it does all of that in a fraction of a second.
It's amazing.
It handles straight lines, sweeping curves, tiny internal holes, all with zero distortion to the material.
Okay, that mechanical breakdown helps a lot. It explains how the machine actually achieves the cut. But the source guide focuses very specifically on the single-ply aspect of this technology.
Right, meaning it cuts one layer at a time.
Yeah, one layer. And honestly, if I am running a factory, my immediate instinct is to just stack 100 layers of fabric on that vacuum table and cut them all at once to save time.
Which makes sense. And multiply cutting, where you do stack dozens or hundreds of layers, is a fantastic tool for sheer volume.
So it does exist.
Oh, yeah.
Huh.
If a brand is producing, say, 20,000 identical pairs of standard blue jeans, a multiply cutter is absolutely the right tool for the job.
Okay, but modern consumer demand doesn't always look like massive runs of identical items anymore.
Exactly. The single-ply cutter is designed to solve what the industry calls the flexibility paradox.
The flexibility paradox.
Like, what happens when a manufacturer needs to make a custom prototype for a single client? Or maybe a limited batch of aerospace insulation panels that involve 10 completely different sizes.
Setting up a multiply machine for a small run like that sounds like an absolute nightmare.
It really is.
You'd have to, create physical templates, adjust the tension for a huge stack of fabric, prep the whole machine just to cut a few items. I suppose it's kind of the difference between a traditional industrial printing press and a high-end smart printer.
Oh, I like that analogy.
Like, if I need to print 10,000 copies of a daily newspaper, I fire up the massive printing press. It takes hours to set up the metal plates and get the ink flowing, but once it's running, it churns out identical copies with incredible efficiency.
Right, perfect for volume.
But if I need to print one custom marketing flyer and then immediately switch to printing a high-resolution photograph and then print a multi-page legal document, that giant printing press is totally useless.
It would take you days.
Exactly. I need the smart printer. I just send a new digital file and the machine adapts instantly.
That analogy perfectly captures the strategic value here. The single-ply cutter gives a factory the agility of that smart printer.
Because it's entirely digital.
Right, because there are no physical dies or heavy mechanical setups to change out. A factory can cut a prototype for, let's say, an automotive seat cover, and literally 3 minutes later, load a completely different CAD file to cut a custom piece of marine upholstery.
Wow.
The transition time is virtually zero.
Okay, I understand the flexibility, but because this machine is jumping between incredibly complex, customized jobs, the stakes for getting it right seem much, much higher.
Oh, they are.
The guide spends a significant amount of time discussing the foundation of manufacturing quality, which really boils down to precision. And it contrasts this automated precision with the inherent risks of cutting things by hand.
Yeah, and we mentioned operator fatigue earlier, which is, the most obvious risk. But manual cutting introduces these tiny micro errors that compound over time.
Micro errors.
Yeah. A physical cardboard template placed on a sheet of material might just shift by a millimeter. Or a worker might misread a mark on a measuring tape, or even angle their cutting knife slightly to the left just because they are leaning over a wide table.
To be fair, a millimeter shift doesn't really sound like a catastrophe in the grand scheme of things.
That is exactly the illusion that sinks factory budgets.
Really?
A single cutting error rarely stops at the cutting table. Let's actually trace the timeline of a minor error as outlined in the guide.
Let's do it.
Imagine a manual cutter working on a piece of really expensive automotive leather. It's 3 p.m. on a Thursday. They've been cutting since 6 a.m.
So they're tired.
Exactly. Their hand cramps slightly, the template shifts, and a tiny alignment notch on the leather is cut, say, a 1/4 inch off target. The cutter doesn't even notice. So that leather gets bundled up and sent to the sewing department.
So the error is already migrating down the assembly line?
Yep. The sewer receives the piece on Friday morning. They try to align the notch with the adjoining piece of leather, but obviously it doesn't fit.
Because it's a 1/4 inch off.
Right. But the sewer is under a strict quota, so rather than rejecting the piece and falling behind, they just pull and stretch the leather forcefully to make the edges meet, and they sew it together anyway.
Oh man, so they are essentially baking the error right into the product.
Exactly. Now that stitched cover goes to the assembly department, where a worker has to stretch that leather over a rigid foam car seat frame.
And it's not going to fit.
No. Because the leather was stretched unnaturally during sewing, it doesn't fit over the frame smoothly. The worker wrestles with it, uses excessive force, and creates a visible buckle in the material. Finally, it reaches quality control on Friday afternoon.
And let me guess.
Yep. The inspector sees a warped, buckling car seat, and they reject it entirely.
That is just painful to visualize, because you haven't just wasted that single piece of leather from Thursday. You have wasted the thread, the foam, the hours of labor from the cutter, the sewer, the assembler, and the inspector.
And the downstream nightmare continues even after that.
How so?
Well, to replace that seat and actually meet the client's shipment deadline, the factory now has to authorize emergency overtime. The cutter has to pull a fresh, expensive hide of leather from inventory and start completely over. The sewer has to stay late.
Wow.
The financial cost of that 1/4-inch mistake on Thursday afternoon has just multiplied by a factor of 10. And that's while also risking the factory's reputation if that flawed seat had somehow made it onto a delivery truck.
Okay, so when we talk about precision here, we aren't just talking about making something look nice. So the single-ply cutter, by perfectly executing those CAD file coordinates every single time, it essentially operates as an insurance policy for the rest of the factory.
That's a great way to put it.
It ensures the sewing and assembly departments are always working with mathematically perfect pieces.
It creates absolute predictability. When you remove the variability of human physical performance from that very first cutting stage, you protect the factory's entire timeline, its labor pool, and its materials.
Which means we need to look at the financial reality of buying one of these CNC machines. Because protecting the timeline is great, but a factory owner has to actually justify the massive capital expenditure.
Always comes down to the math.
Right. And the guide provides some hard math on labor efficiency using a hypothetical startup. They present this scenario where a small factory has 3 employees dedicated solely to manual cutting.
Yep.
If the fully loaded cost of each employee is roughly $45,000 a year, that manual cutting department costs $135,000 annually.
Right.
By installing an automatic single-ply cutter, the guide suggests they might only need one primary operator to manage the machine, which yields a gross labor efficiency of $90,000.
The math is definitely compelling.
Yeah.
But the source material is very careful to clarify that automation does not mean human beings simply vanish from the factory floor.
Well, I want to challenge this narrative just a bit.
Okay, go for it.
Because the guide presents this very neatly, you
Yeah.
know? You drop from 3 cutters to 1, but you aren't firing people, you are just quote-unquote upskilling them.
Right.
But if I am a factory owner and I just spent a small fortune on a highly advanced robot that does all the cutting,
Yeah.
why am I still paying a full-time salary to someone just to stand there and watch it? I mean, the machine is doing the labor.
Well, the machine is doing the physical execution, yes. But the machine is entirely blind.
What do you mean?
It does not know if the material being fed onto its table has a massive stain on it. It does not know if the digital file it was sent is actually the correct updated version for the client.
Oh, I see.
So the human role shifts from the manual grind of holding a blade to complex system management. The operator is responsible for loading the heavy rolls of material, monitoring the vacuum tension, inspecting the raw fabric for defects before it is cut, and ensuring those CAD files are properly prepped.
So you are paying for their cognitive ability to manage a digital workflow rather than just their physical stamina.
Exactly. They become a technician rather than a manual laborer. And while that labor efficiency is a significant factor in the return on investment, the savings generated by material utilization, that is where the financial argument becomes truly undeniable.
Okay, let's talk about material waste. Because we aren't just talking about inexpensive cotton here. The industries using these machines are cutting highly expensive raw materials.
Extremely expensive.
Think about, top grain leather for luxury furniture or specialized marine vinyl or those technical composite textiles used in aerospace like carbon fiber. Every square inch of that material has a high dollar value attached to it.
And when humans cut by hand, they place the physical templates on the material, and they usually try to leave enough space between the shapes to avoid making mistakes.
Which makes sense for a person.
It does, but it is an incredibly inefficient use of space. But before the CNC machine makes even a single cut, this specialized piece of technology called digital nesting software takes over.
And I found the explanation of nesting absolutely fascinating. How does the software actually calculate that layout?
So it basically treats the raw material as a blank digital canvas. The software takes all the disparate CAD shapes required for an order. So the large panels, the small pockets, the curved collars, the thin little
And
straps.
all the puzzle pieces.
Exactly. And it runs algorithmic geometry, checking literally thousands of possible permutations every second.
Thousands.
Yeah. It rotates pieces by fractions of a degree, sliding them together, nesting small shapes into the negative space of larger shapes. It even configures pieces so they can share a single cut line.
That's wild.
It achieves a mathematical density that a human brain simply cannot compute.
It is essentially playing an infinitely complex game of Tetris, but with irregular shapes moving at the speed of a processor.
Yes, algorithmic Tetris.
Let's look at the financial breakdown the guide provides for this algorithmic Tetris. They use a baseline of a factory spending $500,000 a year on raw materials.
Okay.
If the digital nesting software finds just a slightly more efficient layout and creates a mere 2% improvement in how that material is utilized, that tiny sliver saves the factory $10,000 a year in material that would have otherwise just gone into the dumpster.
And if the nesting software gets them an 8% improvement, which is actually highly common when transitioning away from manual cutting, that is $40,000 saved annually.
That's huge for a small factory.
It is. Now, apply that exact same math to a much larger facility. If a manufacturer is spending $3 million a year on specialized materials, a 4% improvement through digital nesting saves them $120,000 every single year.
That's unbelievable.
A machine practically pays for itself just through the scraps it doesn't create.
Now, the numbers scale dramatically, obviously, but I imagine the implementation looks entirely different depending on the size of the business. Like, a two-person startup making bespoke backpacks cannot utilize this machine in the same way a massive Tier 1 automotive supplier does.
No, the strategy is very different.
So how does the value proposition change across those different tiers of manufacturing?
Well, for a startup, purchasing a single-ply cutter is really about acquiring instant scalability. They're basically buying a permanent digital production capability.
How so?
So if they design a custom backpack, cut it, and ship it to a client, and then that client calls back 6 months later wanting an exact replica, the startup doesn't have to go digging through some dusty storage closet for a physical cardboard pattern that might be bent or damaged.
They just open the computer.
Right. They pull up the saved CAD file, hit run, and the machine produces a mathematically perfect clone of the original order. It allows a very small team to punch far above their weight class. They can take on complex prototypes and small batch orders without needing the capital to hire a massive manual workforce.
I can definitely see how that transforms a small business. But what about the behemoths? The giant apparel factories that already own those massive multiply cutters we discussed earlier? I mean, they aren't going to throw out machines that can cut 100 layers of denim at a time.
No, of course not. They absolutely keep their multiply machines for their high-volume baseline production. But what they do is they use the single-ply cutter as a specialized rapid response production cell.
Oh, I see. It makes me think of like a massive global shipping company.
Okay, I like your analogies. Let's hear it.
Well, they have these giant, slow-moving cargo ships that cross the ocean, right? That is their multiply cutter, highly efficient for moving bulk, but absolutely terrible at pivoting quickly. But then that same company buys a small fleet of high-performance speedboats. They aren't replacing the cargo ships. They're just giving themselves the agility to dart into small harbors and complete urgent, specialized deliveries that the big ships simply cannot physically manage.
That is spot on. The speedboat provides agility without disrupting the core business. And we see this dual approach across a massive cross-section of industries today.
Like automotive, right?
Yep. Automotive manufacturers use these single-ply cells for custom interior trim packages. Aerospace companies use them to cut composite acoustic insulation, where literally every gram of weight and millimeter of fit has to be verified.
And you also see it in marine upholstery, high-end footwear, where the geometric shapes of the material are incredibly complex, and medical protective equipment, where having consistent components is literally a matter of safety and compliance.
Absolutely.
But, applying this technology across all these industries reveals what the source material describes as the ultimate hidden benefit.
Ah, yes. The big shift in thinking.
Right, because up to this point in the deep dive, everything we have discussed, saving labor costs, reducing material waste, preventing downstream errors on the assembly line, all of that is essentially playing defense.
It's just about stopping money from leaking out of the factory wall.
Exactly. But the paradigm shift occurs when a manufacturer realizes this automation actually allows them to play offense.
It is not just a cost-cutting measure anymore. It becomes a fundamental growth
Oh,
investment.
right. By automating the most severe bottleneck on the floor, the factory unlocks its own hidden capacity. Let's actually explore the reality of a maxed out factory for a second.
Yeah.
If you run a manual cutting room and your team is operating at 100% capacity, what happens when a massive new client calls and wants to place a highly lucrative order?
They're kind of trapped.
You are. You either have to turn the business away entirely, or you force your existing staff into exhausting overtime that degrades morale and quality, or you outsource the work to a third party, and that eats your profit margins and completely removes your control over the final product.
None of which are good options. But when you remove the physical limitation of manual cutting, that bottleneck suddenly widens. The CNC machine can run continuously, flawlessly, across multiple shifts without ever getting tired.
Right.
So the strategic question for a factory owner is not, how many salaries can this machine eliminate? The much better question is, how much total inefficiency can this system remove from my floor, and what new business does that newly found bandwidth allow us to actually capture?
And if the agility of this machine allows a manufacturer to accept just one major additional contract that they otherwise would have been forced to decline, the financial value of that new business completely dwarfs whatever they saved on scrap leather or direct labor.
Oh, complete.
They aren't just buying a cutting system, they are essentially buying time. Time that they can now turn around and sell to new clients.
And this brings us right to the core philosophy underpinning this entire source text. The future of manufacturing relies entirely on a seamless digital workflow.
Seamless being the operative word.
Exactly. The process begins with a digital CAD design. It moves into algorithmic digital nesting. It flows directly into automated CNC execution, and it results in a permanent digital production record. The automatic single-ply cutter is simply the physical instrument playing the digital sheet music.
It really is the exact moment where lines of code become a physical object you can hold in your hand.
That's a great way to summarize it.
Well, let's take a step back and recap the territory we have covered today. We started with the realization that the simple act of cutting raw material is the great hidden bottleneck of manufacturing.
Right.
We have explored the mechanics of how an automatic single-ply cutter uses intense vacuum pressure, high-speed oscillating blades, and digital coordinates to solve that bottleneck.
Which is still mind-blowing to me.
Truly. And then we detailed how algorithmic nesting plays high-speed geometry to save hundreds of thousands of dollars in wasted materials, and how flawless cutting prevents those catastrophic compounding errors from destroying the assembly line.
And ultimately, this technology gives scrappy startups the power to scale instantly, while giving established giants the agility to unlock hidden capacity and take on totally new business.
It fundamentally redefines the capabilities of a modern production floor, moving it from a space of manual attrition to a true hub of digital execution.
It really does.
Which leaves me with a lingering thought that the source material hints at, but it doesn't fully resolve.
Oh, I'm curious.
Well, we have spent this deep dive establishing that the physical act of cutting is becoming perfectly automated and perfectly consistent across the globe.
Yeah.
So if you are a factory owner and you have the exact same flawless CNC cutting robot as your fiercest competitor across the street, the physical execution of your product is virtually identical.
That's true.
So does the true competitive advantage of a manufacturing company shift entirely away from the physical craftsmanship happening on the floor? Does the battle to be the best manufacturer suddenly rest purely in the minds of the software engineers designing your nesting algorithms and the digital designers creating your CAD patterns? That is a profound question.
If a machine can perfectly cut out 1,000 complex snowflakes without breaking a sweat, does the real genius now lie entirely with the person who codes the shape of the snowflake?
Wow.
Just something for you to think about the next time you look at the intricate stitching on a car seat or the precise seams of your jacket. Thanks for joining us on this deep dive.